So when we started doing the planning sessions for this year's PDS, one of the big things that kept popping up was blockchain, but it was very cryptic. It was just blockchain. What do we want to talk about blockchain? So as we started having our discussions and talking about it, we were talking about, well, we saw this great thing on YouTube, and there's a great professor over here. There's a lot of things going on over here. What do we really want to talk about? But as I kind of talked about in my cybersecurity session this morning, I see a big benefit for us actually talking about these new technologies and trying to see how they actually relate back to what it is we do. So one of the first people that came to mind for me was Austin Roberts. He and I have known each other for several years. Austin worked, I'll give his bio just myself because I know a little bit about him. But so he worked for Propylon for several years and actually worked on their core team. And then left Propylon and started his own company. They're now doing a blockchain-based company, but I knew because of his background with legislative information systems that he knew what we did, and he could take a look at this new technology that he's working in his new business and possibly relate it back to some of the things that we're doing, give us some ideas, try to kind of spark some ideas in our minds about how blockchain might work for us. So I'll introduce Austin. Austin is going to do our presentation today.
Great, thank you. Check. Can you guys hear me? Okay. So yeah, as Jeff said, I'm Austin Roberts. This slide basically says what he just said. I do some consulting through a company called NoteG. Getting some echo. Are you guys hearing? Okay. Yeah, so I do some consulting through a company called NoteG. I work for a while, through that I work for a wide range of companies ranging from the legislative space to the educational space to the blockchain space. And then I have a company called OpenRelay, which is a small blockchain-based startup, and we're trying to get some momentum there. But yeah, as Jeff said, I have several years of experience in the legislative space, about as much experience as anybody in the blockchain space, because it hadn't been there that long. And so that put me in a kind of unique position to do this presentation and talk to you guys today. So the first thing I want to talk about is what problems can a blockchain solve? So, blockchains are kind of the new hotness and everybody wants one and they want it to solve all of their problems. But there are actually only two problems that a blockchain can solve, and if you're trying to solve other problems, you're better off using a database. So if you have a computer science degree, you've probably heard of the Byzantine generals problem. The idea behind the Byzantine generals problem is you have a bunch of armies surrounding a city. And those armies are planning to attack that city and take it, but a coordinated attack will lead to victory, while an uncoordinated attack will lead to defeat. So they won't be able to take the city unless everybody attacks together with some sort of plan. We were talking about planning in the last presentation. Planning is important for Byzantine generals as well. But how do you agree to a plan when you are positioned around a rather large city? Well, you can send messengers, but messages can be delayed or lost. If you send a messenger from the east side of the city to the west side of the city, you as the general who sent that messenger have no way of knowing really that that message was ever received on the other side of the city. The messenger could have been captured, they could have been killed. So you can't really be sure that your message ever got to the other side of the city. The other thing is that messengers are not always trustworthy. So when some shady character shows up in your camp and says that the general across the way says we must attack after sunset, maybe that guy actually came from the city. Maybe he's not reporting for the general on the other side of the city, and he's actually telling you, you should attack at this time, and you'll be the only army attacking, and the other armies will be attacking at other times. Anyway, they could potentially be throwing you off, and you have no way of knowing, unless you've met this messenger personally, that this guy actually came from the other general. So when you have this distributed set of people who can send messages to each other, but you don't know if your messages got where they're going, and you don't know if the messages that are getting to you are trustworthy, how can you know if everybody's on the same page? So the same challenges apply to networks. So networks probably aren't planning an attack on a city, but when you have distributed systems that need to agree on something, like a plan of attack, or everybody's account balances, or what IP address should be resolved when you type in google.com. Those are multiple systems that need to agree on something. Additionally, each participant can have their own interests. So you might have, if you're talking about account balances, somebody might try to do things that would increase their account balances unfairly. Or if you're talking about something like DNS, somebody might report, oh yeah, google.com, you should come to this IP right here, and I'll handle that request for you. So, and again, on modern computer networks, messages can be lost. So there's techniques that we use to prevent against messages getting lost, but particularly if you're on a peer-to-peer system and you expect to relay a message to one peer and have them broadcast that to lots of other peers, once you send off that message, just like the Byzantine general, you don't know if that message got to everyone it was supposed to go to. The next point is that the network layer is not always trustworthy. I am presenting here from conference Wi-Fi. I don't know how trustworthy the hotel's Wi-Fi actually is. It may be that I make a request out to some site on the internet, and if somebody at the hotel is doing something shady, I might get a response from the hotel instead of whoever's supposed to be sending me that response. So again, we have the problem of how do we know if everybody's on the same page when we have distributed systems with latencies, no sure way to know that the message got where it's supposed to go, and no sure way that you can trust messages that you're receiving. How do we know when everybody's on the same page? So modern technology has given us some partial solutions. We have cryptographic signatures that go a long way towards telling us, yes, this message came from the general on the other side of the city, but that also just kind of removes the question one layer. And so, yes, I know this message was signed by this particular key, but how do I know that key came from that general? Networks are fast, but we still have latencies, and particularly when you're dealing with peer-to-peer networks, you don't know how long it's going to take your message to propagate across a network to a bunch of different peers. And then we have things like TCP ACKs and sliding windows to make sure that messages don't get dropped. But again, those only get you as far as your next peer in a peer-to-peer network. They don't connect you to everyone else on the network. So there's a heuristic solution to the distributed consensus problem called proof of work. And when I say a heuristic solution, that means it is not perfect, it is not guaranteed to give you the correct result every time, but it gets you close enough for the economic purposes tried to solve, or that blockchains are trying to solve. So proof of work was introduced by the Bitcoin blockchain, which I'm sure most of you have heard of. Bitcoin was really the first modern blockchain. There were a couple of things that could arguably be called blockchains before Bitcoin, but none of them had proof of work, so they didn't really achieve the distributed consensus problem. The goal of Bitcoin was to agree on account balances. So it's fairly simple. They just want to say, account A has 50 Bitcoin, account B has 10 Bitcoin, account C has half a Bitcoin. And importantly, one of the goals is that nobody is in charge. So account balances are easy if you put somebody in charge. If everybody just agrees, we have a bank, anytime I want to move money from account A to account B, I'm going to go to the bank and they're going to write it down on their ledger and they're going to transfer that money. That's easy. But that bank is what we call a trusted intermediary. That means you have to trust this bank that they're going to keep track of your ledger correctly and that they are going to transfer account balances like you want them to. Generally speaking, because of the society that we live in and the systems of governments that we have in place and the rules that we have around banking, they're pretty good at that. But if we could disintermediate that problem and make it so that nobody is in charge and we don't have to trust anybody to manage those account balances, I think it's good to be able to do that. So the solution that Bitcoin put into place is basically that for a proof of work blockchain, everyone agrees to a set of rules. I don't think that's on. Was that on? No? Okay. Everyone agrees to a set of rules. And if you're participating on the Bitcoin blockchain, you may not realize that you've agreed to this set of rules, but you have presumably downloaded a Bitcoin client that is connecting you to the Bitcoin network, and that Bitcoin client is enforcing this set of rules on your behalf. So when you first download your Bitcoin client, the first thing it's going to do is download the historical data associated with the Bitcoin blockchain, and it is going to validate that historical data against the agreed upon rules. Once it has validated the historical data and has an accurate view of what the state of the network is today, that is to say, what are everybody's balances on the blockchain, you are able to contribute new data to the blockchain so long as it follows the rules. And in addition to contributing your own data, you also receive data from other users, which your client will then validate to make sure that the other users are also following the rules, and if they're not, you will not consider their data to be valid and it will be discarded. So, this is our image of a blockchain that we're going to be using today. And so here we have, the blockchain is comprised of chunks of data called blocks. And you see we have two blocks here. So we have this one up here and this one down here, and they look the same. They have pretty much the same pieces of data. The blockchain is comprised, or each block is comprised primarily of a set of transactions. And transactions are going to describe changes to the state of the network. So in the case of Bitcoin, we're moving 5 Bitcoin from account A to account C. That is a transaction. And most of a block is going to be comprised of a bunch of different transactions. There are several other metadata fields associated with a block in the blockchain, and we'll talk about those as we go. So blocks are added to the blockchain periodically, and the way that you add a block to the blockchain is, again, you create a chunk of data that has mostly transactions to it, has the other metadata fields, and then it has this parent field. And the parent field is going to have a reference to the previous block, and that is going to be, once that new block gets sent out to the network, and it has that reference to the old block, you now have your chain. You have each block referring to the block before it, referring to the block before it, on back to what's known as the Genesis block. So valid blocks have to have valid transactions. So up here, all of these transactions have to be validated by every network, or every member of the network that accepts this block. So in the case of Bitcoin, for a transaction to be valid, if we use the case I mentioned earlier where account A has created a transaction to send 5 Bitcoin to account B, that transaction is not valid if account A doesn't have at least 5 Bitcoin. So if there is a transaction in there that says, transfer more out of my account than I actually have, the entire block is going to be considered invalid by the rest of the network. The other aspect, and this is where proof of work comes into play, is that the block is valid if the hash of the block starts with enough 0 bits. So if you're familiar with cryptographic hashing, the basic idea is that you take an arbitrarily sized piece of information, you run it through a mathematical function, and it spits out a predictably sized piece of information. So in the case of Bitcoin, it uses the SHA-256 algorithm, and it's going to spit out a 256-bit piece of information that is determined by all of the transactions and all of the metadata about the block. So one of the important things to understand about a cryptographic hashing function is that if you change that block in any way, it will change the hash of the block in an unpredictable fashion. So you won't be able to guess what changes you could make in order to make the hash look the way you want it to. And because you have to have enough 0 bits at the start of 0 bits at the start of your hash of the block, that means that you have to try a whole bunch of different permutations of a block in order to find something that the rest of the network will consider to be valid. And that's called, the number of 0 bits that you have to have at the start of the hash is called the difficulty. So if you have to have the hash of the entire block match, have a certain pattern at the beginning, the way that you can do that is by manipulating this value over here called the nonce. The nonce is a piece of information. It's 256 bits, just like the hash. It doesn't matter what's there, except that you can change what's there in order to make the hash of the block come out to 250, or to come out to have a certain number of leading zeros. And the way that you do that is by trying a whole bunch of nonces until you find something that works. I heard a couple of people who were sitting over at that table earlier, but I don't think they're there right now, talking about how they were trying to build a computer and GPUs are really hard to come by and really expensive these days. That's because lots of people are buying GPUs and using them to hash blocks for the blockchain and come up with nonces that will give them a certain number of zeros at the start of their hash so that they can claim a block. And that would make them the miner here in this field. So the people who are searching for those nonces that would make a block valid are called miners. So the network will recognize the valid block with the most valid ancestors. So in this case, we just show 2 items here, and this would presumably be the latest block because there's nothing pointing to it. But this has a field pointed to the next block, which has a field pointed to the next block, and so forth. So whichever block has the most valid ancestors represents the current state of the network. As we noted, the people who are searching for those nonces are called miners, or the computers that are searching for those nonces are called miners. They get to put their address in here, and they get to claim what's called a block reward. So in the case of Bitcoin, right now, if you found a Bitcoin block, you would get 12.5 Bitcoin for your troubles of trying to find a nonce that would give you a valid hash. So the general process for block mining is that people or computers called miners hash the block. If the hash fails the difficulty requirement, which means they have enough zeros at the front, then they change the nonce and repeat. And in practice, they do this a whole bunch of times in parallel using either GPUs or highly specialized hardware built specifically for this purpose. If the hash meets the difficulty requirement, then they take that block and they broadcast it to their peers. Once their peers receive the block, they validate the hash to make sure that it meets the difficulty requirement, and then they go over transaction by transaction to make sure that all of the transactions there are valid, that nobody's sending Bitcoin that they don't have to somebody else. This is one of the things that adds latency to a peer-to-peer network, is that nobody wants to broadcast an invalid block to their peers, or their peers will disconnect from them and they won't be able to participate in the network anymore. So in order to, but before they will broadcast the block to their peers, they first want to validate it and make sure that it's valid, which takes time and adds to the latency of which it takes the block to propagate across the network. So once a block has propagated across the network, that is to say, most of the peers on the network have that block, the network recognizes all of the transactions in that new block as part of the state. So when account A that I mentioned earlier wanted to send 5 Bitcoin to account B, they broadcast that transaction to the network. But until that transaction gets included into a block by a miner, it hasn't happened yet. The network considers things to happen once a transaction has been confirmed into a block, not just because somebody has broadcast their intent to do something to the network. The other aspect of block mining is the periodic difficulty adjustment. So I've been vague about how many zeros you have to have at the start of your hash, and the reason for that is it changes. So in the case of Bitcoin, every 2016 blocks, and blocks come out every 10 minutes, so this comes out to about every 2 weeks, all of the miners stop for a second and they say, okay, how much time did it take for us to produce this last 2016 blocks? They take the amount of time it took and the difficulty over that period of time, and then they they calculate a new difficulty that would mean that the Bitcoin blocks get to keep coming out every 10 minutes, regardless of the hashing power. And the hashing power typically goes up from week to week, but they adjust such that new Bitcoin blocks come out about every 10 minutes. So the primary benefit and the big innovation of the Bitcoin blockchain was this concept of distributed consensus and how you can have a network of peers agreeing to something without having anybody who's in charge. The other benefit to a blockchain is this concept of unassailable audit logs. So here we have a blockchain with 5 blocks, and we can assume that there's other blocks below this guy, but we've only represented 5 here. And I don't know if you can see on the screen, but that transaction right there is red. So the idea here is that this is the latest block, and I just realized that 4 blocks ago I made a mistake, and I want to fix it before my boss or before my client finds out about it. Well, we have a problem if I want to go back and change the history of this system. In a traditional database, if I had sufficient privileges, I could just go in and I could run a SQL query that would adjust some record in a database. But in a blockchain, we have math that prevents us from doing that. So we took the hash of this block and we stored it in the next block, in the parent field. So then we took the hash of this block, which included that hash, and stored it in the next block, and so forth. So if I want to change this one field in this one block, I'm changing the cryptographic hash of this block, which means I have to change the cryptographic hash of the block that refers to it on up through the entire rest of the blockchain. So I can't just go back and make a change. Now, if I was the only one running a copy of this blockchain, then yeah, maybe I could go do that and I could just rewrite all the blocks. But if anybody else knows about the blocks on the blockchain, or even if I've just published the hash of a block periodically, I can't come back and make a change without changing the hash that I've already published, and people are going to go, wait a second, this hash that you published earlier doesn't show up in your blockchain anymore. So to achieve these unassailable audit logs, you have to periodically publish your block hash in a place that other people are going to have access to it and be able to call you out if you go back and make those changes. It allows you to subsequently prove the entire state of the blockchain at that particular block just by publishing 256 bits. That's 32 bytes, or not very much data. You can put it in a tweet, which is one of the suggestions I have down here. But one of the neat things about publishing a block hash is that it reveals no information about the data that it represents, but it allows you to prove the data that you had at that time to anybody who wants to challenge you on it and ask for proof of your audit logs. So you can publish a block hash anywhere that doesn't let you edit the stuff that you've posted. So Twitter doesn't let you edit the stuff that you've posted. You can delete stuff, but if you have a tweet that you made, nobody can really say, oh, well, you changed that. Now, if you don't trust Twitter themselves and you think they might be changing those things, you could publish your block hashes to other blockchains. So you could publish a block hash to the Bitcoin blockchain or the Ethereum blockchain, and I'll talk about Ethereum in a minute. And once your hash is stored there, you have tons of computational power protecting it and proving that you can't have changed it after the fact unless you had billions of dollars worth of computing power to go back and make these changes. So Ethereum is a blockchain that came out several years after Bitcoin, and it takes several of the concepts from Bitcoin and it builds upon them. So the goal of Ethereum is not to represent a simple ledger, but to to achieve consensus for arbitrary applications. So sometimes I tell people that Ethereum is the slowest computer in the world, but it's just one computer, and anybody can run stuff on it, and everybody knows that it's going to run the way it's supposed to run, and nobody can cheat that. So Ethereum and Bitcoin are similar in that they both use proof of work, although Ethereum uses a different proof of work algorithm than what I described earlier. So it's not take a hash and check the number of zeros at the front. It's more complicated than that, but it uses a similar proof of work algorithm. They both use peer-to-peer networks, so there is no central authority. There's nobody in charge who can say, this is okay, this isn't okay. When something is happening on the Ethereum blockchain, so long as it complies with the rules that everybody agreed to up front, that constitute a valid block, there's nobody who's going to tell you, no, you can't do that. And they also have concepts of both block and transaction level validation. So, blocks are going to be, is the proof of work correct? Does it have a valid parent? And then the transaction level validations are going to be quite a bit more complicated than they were at Bitcoin, because it's not a simple matter of transferring 5 Bitcoin from A to B and making sure that A had the 5 Bitcoin they said they'd have. Since it's arbitrary applications, the validation gets a lot more complex. Some of the big differences between Ethereum and Bitcoin, where, as I said, where Bitcoin represents a fairly simple ledger, Ethereum represents complex applications called smart contracts. One of the next big differences is the block time. So as I mentioned, Bitcoin adjusts the block difficulty such that blocks come out about every 10 minutes. Ethereum maintains a block difficulty such that new Ethereum blocks come out about every 15 seconds. So Ethereum blocks happen much more rapidly than Bitcoin blocks. One of the next items is transaction complexity. So with Bitcoin, all you're doing is moving 5 Bitcoin from account A to account B. There's a little bit of complexity that can happen there, but it's not a big deal. And there's not, one transaction isn't going to be wildly more complex than the next. In Ethereum, you have a Turing-complete programming language. You can have for loops and while loops and recursion. So things can go off the rails on an Ethereum transaction, and that computational complexity is represented in gas. And the person who submits a transaction has to pay for that gas using Ether, which is the primary token on the Ethereum blockchain. The other thing that Ethereum will allow you to do is store arbitrary data. So where Bitcoin just lets you store account balances, the smart contracts that are doing these computations can also store data on the blockchain that will be available the next time the smart contract runs. So the public Ethereum blockchain has been running for about 3 years now, and there are several big applications that have come up over that time. So ENS is an answer to the DNS system, so it is an attempt to provide a naming system on the Ethereum blockchain that nobody is in charge of. So there's no ICANN of the ENS system. There is just a smart contract where anybody can go and register a name. Then they have that name and they can point it at whatever they want, whether it's another Ethereum smart contract or a website somewhere. ENS lets you name things. DAI is a complex system of contracts that creates what they call a stable coin. So if you guys have been paying attention, back in January, Bitcoin was trading for about $20,000 and Ether was trading for about $1,400. Today, I haven't actually checked the prices today, I probably should have, but Bitcoin is trading for somewhere less than $6,000 and Ether is trading somewhere less than $200. So they have lost a ton of value. And if you're trying to build a business that operates on the blockchain, it's nice to have somewhere that you can store your value that doesn't fluctuate like that. Back in January, 1 unit of the DAI token was worth $1. And today, 1 unit of the DAI token is worth $1. And so it has managed through a system of complex contracts and economic incentives to maintain its value at $1 as the price of the currencies behind it have tanked. The next item, or the next application is called 0x. 0x is a decentralized trading system. So if you wanted to trade Ether for DAI, for example, you could find somebody who wanted to trade DAI for Ether, take a transaction to the 0x contract, and trade that without any trusted intermediary. There's no New York Stock Exchange, there's no NASDAQ. You can take those buys and sells and exchange them directly on the blockchain without having to trust anybody to facilitate that. The next one is called Augur. Augur is a decentralized prediction market. It allows you to bet on things anywhere from sporting events to the outcome of political policies or government policies. And you can see how people are betting on those and get some information on how people think these things are going to go. The next item is called the Basic Attention Token, or BAT. BAT was created by Brendan Eich, who was the creator of JavaScript and then later the CEO of Mozilla. The purpose of BAT is to allow people who are consuming content, whether it be blog posts or YouTube videos or things like that, to compensate the people who are producing that content without having to go through advertisers. So essentially, you can buy BAT tokens, set up a browser plugin so that it will automatically pay the content producers without you having to do anything behind the scenes. The next item is called Gitcoin. Gitcoin, I think, is a really neat little application. They call them dApps, for decentralized apps. And what it does is it allows people who want a feature or want a bug fix on an open source application to put a bounty to be paid in whatever Ethereum token you like to whoever implements that feature or whoever fixes that bug. So it gives a way to compensate open source contributors for their efforts. The next item is called BZX. BZX is a decentralized lending platform. So kind of like with 0x, where if you wanted to trade 2 tokens, with BZX, if you wanted to borrow a token from somebody and had some collateral you were willing to give them in the meantime, you could negotiate terms on the blockchain, and the blockchain will enforce the terms of those loans. So if you don't make your repayments, it takes the collateral and gives it to them. Or if the price of Ether has fluctuated too much with respect to the price of DAI, it will liquidate your collateral and pay off the lender. And again, this is all disintermediated, which is to say there is nobody in charge of those loans. It's a peer-to-peer type thing that is enforced, the rules of which are enforced by the network. Finally, we have CryptoKitties. So CryptoKitties is not quite like the rest of these. CryptoKitties is a game where you can buy, sell, and breed digital cats. So those apps that I just talked about are all on the public Ethereum blockchain. And the public Ethereum blockchain uses proof of work. But Ethereum also has this concept of proof of authority for private blockchains, or for less blockchains with a different set of security requirements. So proof of authority is an alternative to proof of work. And the way it works is, instead of having to do some complex calculation to validate, to show that a block is valid, all you have to do is have one person out of a list of trusted authorities sign the block. So they have a public-private key pair, a list of public keys for authorities are known to the network, and then all you have, they sign a block and everybody considers it to be valid. So this is, of course, faster. And in fact, a proof of authority blockchain on commodity hardware can handle about 200 transactions per second, whereas the public proof of work blockchain can handle about 15 transactions per second. Because there are no computationally complex calculations going on, proof of authority blockchains are far less costly. And they have much lower environmental impacts because you're not using so many GPUs that it makes them hard to find and drives up the price, going 24/7 trying to find nonces to mine your blocks. So, like I said, you can potentially have multiple authorities. It's not necessarily the case that you have a single authority on a proof of authority blockchain, but you have a finite set of authorities. And one of the neat things is that a proof of authority blockchain gives you the same application layer as proof of work. So what that means is that all of those distributed applications that I just showed you, ranging from, what did I have first? ENS down to CryptoKitties, all of those can also run at the application layer on a proof of authority network. So all of the tools that were used to develop those applications are available to develop proof of authority applications. Sounds like someone's having fun up there. Now, there are, of course, drawbacks to proof of authority networks, and this is the reason that the public Ethereum network does not run on, it uses proof of work instead of proof of authority, and that's that you have to trust somebody. So you're back to having to trust an intermediary. You still have that unassailable audit log. If you have those hashes of your blocks and you've been publishing them somewhere, but now you have this risk of censorship. So in a proof of authority blockchain, if somebody says, I really don't like this guy, I'm not going to let him do any transactions on my network, he's locked out. He just can't get any transactions into a block. On a proof of work blockchain, if somebody says, I don't like this guy, I'm not going to include any of his blocks in the blockchain, there's thousands of other miners who will include his blocks in the blockchain and they will still get through. So no one entity can say, these transactions aren't good, I'm going to discard them. You have your public set of rules about what can go in blocks, and eventually somebody will include them. So, finally getting to legislatures, so you're only 38 minutes in. So, practically speaking, I don't think proof of work has much place in legislatures. I think proof of authority has some utility in legislatures because it gives you those audit logs. And as Jeff mentioned earlier, I work for Propylon, and Propylon has some great software that gives you really good audit logs, but they are not mathematically protected in the way that a blockchain's audit logs are mathematically protected. One of the other things that you could do within a legislature is you can have multiple authorities. So, as I noted earlier, you can have alternating authorities, so each authority gets to sign blocks periodically. You could potentially have each caucus run their own authority nodes. So you couldn't have the minority party complaining that the majority party didn't give them some piece of information if all of that is flowing through, if the minority party and the majority party each get to run their own authority nodes, they all get notified about everything that happens within this blockchain context. The other thing is that because we have smart contracts, we get to have validated workflow rules. So you can have the actions that you take be represented as smart contracts. Those smart contracts can implement rules and not just record that something happened, but actually show that the conditions were met, and they can, as you take one action, they can set up the state for the next action. So you can potentially apply this to chamber process. So you can do things like bill introductions. That could be a smart contract where it records information that a bill was introduced and maybe moves the bill object into whatever the next state it's supposed to be in is. You could do things like committee assignments, readings, testimony, amendments, passage. You could bring the executive branch in on this and have the governor sign things on your blockchain or veto things on your blockchain in order to have an end-to-end audit log of all the things that have happened to a particular bill as it makes it through the chamber process. You could potentially use a blockchain within a bill drafting context. I would recommend using it for metadata tracking and not for tracking the bills themselves. Blockchains are good for small pieces of information. They are not good for megabytes or gigabytes of volumes of information. So you probably don't want to encode your statute on a blockchain. You probably don't want to have your bills on a blockchain. But what you could do is, when a member comes in and requests a bill, that request goes on the blockchain so that you have a record of this bill was requested. When that request gets assigned to a revisor, you have a record that that request was assigned to this person. When a bill gets introduced in chamber, that can come back to the bill drafting system and be recorded so that this bill got this bill number when it was introduced. When people request amendments, you can track, again, the metadata about those things within a blockchain, while still probably keeping the actual text of the bills and the amendments and the statute somewhere not on your blockchain. Now, what you might want to keep on your blockchain is what sections of the statute a given bill is amending. Because if you have that, then you can connect the dots and say, okay, we currently have 5 bills that are all attempting to amend the same section of statute. And if you know that, then you can get together the revisors who are working on those 5 bills, or if necessary, the legislators who are working on those 5 bills, and get them talking to each other about how these bills could potentially conflict when they all attempt to edit the same thing at the same time. Oh shoot, hang on a second. But one of the other things is electronic signatures. So one of the things that has come out of blockchain technology are these things called hardware keys. So this is what you call a ledger nano, and when I want to send a transaction to the Ethereum blockchain or the Bitcoin blockchain, I would plug this into my computer. My computer would send a transaction to this device. I could see on this tiny little screen what the transaction is trying to do, and I could say, yes, do that, or no, don't do that. And then the keys that are stored securely on this device would sign the transaction, send it off back to the computer, and which could then broadcast that signature to the blockchain. So one of the other, if you want people to sign things on your blockchain, but you don't want to issue them $100 security keys, you could also do on-device keys. So you could say, you could generate a key on a member's device or on a staff member's device, and you can say that this key is associated with Representative Smith's laptop, and this other key is associated with Representative Smith's cell phone. And then if Representative Smith's cell phone gets lost and you have to replace it, you can record on the blockchain that at this point in time we revoked that key, put this other key in place, and that gives you the problem of the answer to the problem of how do we know which keys are associated with which people, because they're stored on the blockchain according to the rules that everybody has agreed to. So once you have these keys, you can sign things with them. You can sign documents. So if a member has to sign a document in order to pass it out of committee, you could use these keys to sign those documents. If you have a voting system that works on the blockchain, you could use these keys to sign the votes that the members are casting. So you could say, definitively, hey, this vote was cast from Representative Smith's, iPad, and unless Representative Smith is going to say, oh, but my iPad was stolen at that point in time, nobody's going to argue that it was signed by one of his devices. You could, and again, getting back to the idea that you bring the executive branch into this, you could potentially have the governor sign bills into law using the electronic signatures that come from these keys. Now, electronic signatures are not new. Electronic signatures are older than me. But the thing that blockchain has done for electronic signatures is that they have created a demand and thus an attempt at a supply of user-friendly key management approaches. So 10 years ago, where did I put that? 10 years ago, a key that did something like this would have cost hundreds of dollars, and now you can find them on sale for 75 or 80. And then there are tools that go into your browser that do key management that are a lot more user-friendly than the tools that we used to have. So You can actually use a lot of those tools without having to use blockchain, but because blockchain technology has been around for the last 10 years, a lot of tools have been developed to help facilitate it. So another potential application of blockchain within the legislative space is for voting. So I know a couple of different legislatures here said that they have implemented new voting systems in the last couple of years. If you wanted to do blockchain-based voting, you could potentially use it for both committee and floor voting. And you could have the members use the devices that they have keys to sign their votes. So that, again, you can say, you know, this vote was signed by Representative Smith's laptop. Beyond that, aside from just signing things, you can have contracts that are able to do things like tally votes. So one of the challenges I had when I was involved with the Indiana's voting system was we have different votes with different types of rules. So we have simple majority votes, we have super majority votes. How do we handle those? And with the Ethereum blockchain, that becomes a fairly straightforward problem that you can just have a smart contract that knows how to implement each kind of vote, tally the votes, and then return a result that it passed or it failed or it tied. You can also do things to automatically progress things through workflows. So if you were voting on a bill that was on final action, you could, if that bill passes, you could send it straight to the governor's desk. If that bill fails, you could send it over to the dead bills pile. Or if that bill has a tie and you're in the Senate, you could potentially send it to the lieutenant governor's desk to have the tie broken. So you can have all of those actions be taken automatically based on the outcome of the vote, all enforced by the blockchain, all with this strict audit log that we talked about earlier. Outside of the legislative space specifically, there are other applications that the government could have for blockchain technology. So I think regulators are really the big place that, you know, within the next 10 years we will see blockchain technology really become a big thing, because they I think generally have much higher auditing requirements than we have even in the legislative space. So regulators could have regulated entities that have to report in through the blockchain. So they could do something like supply tracking. So if you had you know, pharmaceuticals that needed to be tracked from you know, their manufacturer to the vendor to the consumer, you could potentially track all of those moves of a pharmaceutical ingredient on a blockchain. You can also use the blockchain to enforce separation of duties. So if you have a certain job that absolutely must not be executed by the same person who does this other task, you could use the blockchain to enforce that different people are taking those actions. You can also use it for ongoing self-auditing. So think of it as like microtransactions. So every time a regulated entity takes a certain action, they record on the regulator's blockchain that they've done this particular thing, and that regulator has that information and it gets encoded into that unassailable audit log for future use. Some other items that regulators might be interested in are things like licensure. You could track who is licensed to do what the requirements for licensure are. You could track things like the publication of official opinions. Again, you may not want to publish the opinions themselves, but you could use a public blockchain for notification that there is an official opinion that's been published and give information on where to find it. Similar with public notice requirements. You know, if a particular address is going to be rezoned, there might be a public hearing about that, and you have to notify people that there's going to be a public zoning hearing. Anything that has reporting requirements, you could use the blockchain technology to help you with that reporting and help you with the audit logs that need to go along with that reporting. Then if you have things like freedom of information requests, again, you could have your audit logs to help you prove that the information that you are providing is accurate and has not been tampered with. So, overall, there are two big benefits to blockchain technology. Those are the distributed consensus problem and the unassailable audit logs, and then kind of a byproduct of blockchain technology or the user-friendly key management. But again, if you want the user-friendly key management, you don't have to use a blockchain. You can just use some of the subsidiary tools that have come up around blockchain technology. And again, if you don't have one of these two problems, the distributed consensus problem or the unassailable audit log problem, you're probably better off using a database that, as I mentioned earlier, a proof of authority blockchain can handle about 200 transactions per second. How many can a database handle? It's in the thousands. Again, if you don't have one of these problems, the blockchain is probably not the right answer. But if you do have one of these problems, I would like to talk. Does anybody have questions? Sir?
Real quick question. So is a nonce computation always tied to a transaction?
No. A nonce computation is tied to a group of transactions. Okay. So the nonce, you have, if you just wanted to send a transaction off to the network, you would send that off and it would not be official until somebody called a miner grabs your transaction, includes it in a block, and computes a nonce for that block to validate your transaction. So basically every 10 minutes, somebody in the Bitcoin blockchain, somebody finds a nonce that validates a block, and that block will have hundreds or thousands of transactions in it. Yes?
Are these blocks stored anywhere, or is it just passing time?
Yeah, so in Bitcoin, to participate in the Bitcoin network, a node has to have every block. In the Ethereum blockchain, that is not the case. The Ethereum blockchain has checkpoints where basically you only have to have things that happened after this particular point in time, and there are proofs within the Ethereum blockchain that allow you to be confident in that content even though you didn't validate all of the blocks before it. Yes?
Okay, so in Bitcoin or Ethereum, essentially you had said blocks are being created.
Yes.
Are these blocks empty or is there already transactions in them?
So, in order for a block to be considered valid, it has to have, that nonce that causes the hash to come out. When the miner started trying to find that nonce, they had already picked all of the transactions that were going to be in the block. Does that make sense?
Yeah. So I guess what I'm really trying to ask, okay, you had said that so a miner mines a Bitcoin block, they get 5 Bitcoins.
12 and a half. But yeah,
So what did you say?
12 and a half Bitcoin.
Well, that's a lot of money.
It is a lot of money. But usually it's done by what they call mining pools, and they split it across a whole bunch of people who are pooling their hashing power.
So essentially, are these miners, their job is they're really just validating blocks? Is that what they're doing?
Yes.
And
Yes.
they're
So,
getting paid for that?
yes.
Sounds like you're in the wrong business.
For what it's worth, unless you have highly specialized hardware or government subsidized electricity, it is nearly impossible to make money with mining.
That's what I expected.
We got a lot of power
It is a
sitting
very
in
competitive
this room
space.
here, you know.
Matt?
To go back to the sort of, you talk about the complexity too.
Well, we're at session.
Did they sort of artificially make the challenge to create a block more complex in order to quantify?
Yes,
Okay.
so they changed the number. In the case of Bitcoin, and Bitcoin's easier to understand than the Ethereum proof of work. In fact, I don't even understand the Ethereum proof of work. I just know it's more complicated. In the case of the Bitcoin blockchain, every 2016 blocks, the network looks at how long those 2016 blocks took to generate, and they calculate how many zeros have to come at the start of the hash in order for the next set of blocks to keep coming every 10 minutes. And so, even when the first guy launched Bitcoin and his computer was the only one hashing on it, it took 10 minutes per block. And then as more people have started participating, right now, I checked this yesterday or the day before, There are 65 exahashes per second going on the Ethereum blockchain. Exahashes. So that's like 1,000,000 terahashes or 1,000,000,000 gigahashes per second. That is how many people or how many computers are trying to find, or how much computing power is dedicated to finding these nonces. So as the amount of computing power behind it has gone up, the number of zeros that you have to find has gone up as well. Yes?
Okay, so I know there are states out there that are passing legislation statute that making blockchain ledger technologies, they're putting in statute that that's a valid ledger per se. So have you looked at that or trying to understand what's the value of that and what is that going to do for government versus the citizens of some state or?
So I'm not familiar with some of the specific state legislation. Greg might be able to talk to you about that afterwards. I know he follows the legal aspect of it a little bit more than I do. Essentially, I think, to some extent, like I mentioned, you might publish your private block hash into the Bitcoin blockchain or the Ethereum blockchain. If you subsequently wanted to come along and prove in court that you had the data that you actually have, it would help to have some legal recognition that this ledger, has some validity to it. But I suspect there are also questions around, is it legal to have these currencies? Is Bitcoin? Early on, there was a big question of, is Bitcoin a legal currency? And now, the regulatory space has evolved on that such that it's treated like a, general commodity and, taxed accordingly. So, there was a lot of legal ambiguity early on, but a lot of that has kind of settled out more in the regulatory space than the legislative space, though. Yeah.
Being on the front edge of the whole blockchain space, is there something to be that you would consider the next big thing for blockchain? Or is it that blockchain's next big thing is just brought about by how it's applied to other things like government, business, so?
So blockchain right now is a very immature technology. I would compare it to the internet in the late 80s. I think there are a lot of places where using the distributed consensus problem to disintermediate things is going to become a very, very powerful tool. But right now it's very, very hard to use. And so I think really a lot of the things that need to come along in the blockchain space are usability enhancements, not necessarily things that change, to use the internet analogy, TCP existed in the 80s. No, HTTP existed in the early 90s. But it wasn't until the late 90s that, my mom could figure out how to use a web browser. So we've got a long way to go in terms of making these things usable for everybody. And I think Jeff's timer's about to go off and start anyway, I will be around after. I'll probably go to the BB King's thing this evening, and so if you guys have questions, come hit me up. My partner Greg is back in the back, and he is able to answer a lot of the legal questions because he researches that more than I do. All right, thank you.
Great, thank you all.